Hi, hello everybody. Today is lecture number 4 from the course on laser meta-interaction, and today is the next topic on the course, anisotropic media. As I did already at the beginning of the first 3 lectures, I was emphasizing the importance of approximations, and the approximations that are important when I talk about light meta-interaction is the approximation of electric dipole, approximation of continuous medium, linear optical approximation, approximation of isotropic medium, and approximation of node dissipations. And as at every previous lecture I said, the goal of the course is to figure out what do we actually lose accepting these approximations. At the previous lecture we were talking about approximation of node dissipations. Now we go to the next approximation of isotropic medium. What do we expect to be different when we go to anisotropic media? Well, if the medium is anisotropic and we work with electric dipole approximation and approximation of continuous medium that says that light matter interaction is basically given by the vector product, scalar product of the electric field and the polarization which this electric field induced in the medium, and we assume linear dependence between polarization and the electric field, we are not allowed to state anymore that electric field and the polarization are mutually parallel, because we are talking now about anisotropic medium. So it means that in general E and P are pointing into different directions, and it means that this chi is a matrix. So since we are living in 3-dimensional space, it would be matrix 3 by 3. Then if you want to calculate D, it will be a similar case. And if you want to express etc. Yeah. If you want to express this product differently, then you can write also, let's put it K, for each component of the vector of electric displacement you can write this expression, yeah, which will be the law according to which we calculate the components of vector D if we know the matrix epsilon and the components of vector L. What happens very often in literature is people skip epsilon 0 and they skip sum, and then they simply write like this. So it doesn't mean that they're going to apply this law for calculations. It's just to make the notations shorter. It is supposed that this part is also here. I will also follow the same approach. I will skip it from the notations, but if you have to calculate this and get the real number, don't forget about epsilon, of course, and don't forget about summation. That must be there. Now, if you take this situation and try to apply approximation of node dissipations, like we did before, assuming the divergence of the Poynting vector is 0. So we do steps as we did before. We look at the at this divergence. We notice that this divergence is equal to this expression, as we did at the first lecture. We again would like to emphasize that this part would depend only on mu, and this part will depend only on epsilon. Mu is not very important for us for our case of light matter interaction. because we use electric dipole approximation, and the properties of media are described by epsilon. So we focus on this term, and we would like to know which consequences the approximation of no dissipations will have for epsilon. Then I take this term and define Ek as 1 over 2 k exponent then obviously k epsilon then we substitute those expressions into this product, and what we get is I omega divided by 4, and then we have to, of course, make summation minus Ek dk exponent minus I2 omega t plus Ek complex conjugate dk complex conjugate I2 omega t plus as we emphasized at the very first lecture, these two terms do not contribute to irreversible energy transfer from light to matter because they oscillate in time. And if you average over enough number of periods, you will see that these terms will be averaged to 0. And then here, these two terms may contribute to the dissipations. And if you want to satisfy the condition that divergence of the Poynting vector is 0, then you have to stick to the condition that this expression is valid. And at the end, if you rewrite this expression a bit differently, so if you want to satisfy this condition, you can see that this equality can be represented slightly differently than and this chain is valid only if epsilon KL is a Hermitian matrix. So basically we repeated the very same derivation, but not for scalar, but for matrix, and found that in case of no dissipations, epsilon becomes Hermitian matrix. Well, what are the other consequences of the fact that the medium is anisotropic? Well, imagine that we have electromagnetic wave that propagates in the direction of the axis. It means that we can neglect actually electric field along the z-axis, and we, instead of working with matrix of the electric permittivity 3 by 3, we can reduce this matrix to the matrix 2 by 2. And what we also do, we for simplicity diagonalize this matrix, so we make sure that we only have only diagonal components and not off-diagonal components here. And now in this situation, just imagine that if after we diagonalize the matrix, and diagonalization simply means finding right coordinate system. So after we've chosen right coordinate system and diagonalized the matrix, we found that epsilon xx is not equal to epsilon yy. It means that refraction coefficient for light polarized along x-axis is not equal to refraction coefficient for light polarized along y-axis. And this phenomenon is called linear bifrigence. In particular, it's shown on the example of calcite crystal. You can see doubling of an image. So imagine that you're looking through such a crystal at a certain stripe, and that there is a ray from sun, and here there is an eye. Then eye picks up an ray from the source of light, and intuitively we think that this stripe is here because our eyes neglect refraction. But now if we take a medium with linear bifrigence, imagine that for this polarization, so that polarization like this, we will have refraction coefficient n prime, and for this polarization like this, we will have refraction coefficient double prime, and they are not equal one to another. So now the law of refraction will look differently. And our eye will get an impression that object is at different point. So basically it would be shifted in space. So basically this is the origin of the fact that we have doubling of an image. It's called linear bifrigence. It's a different refraction coefficient for two waves which are linearly polarized. Since, as we had discussed during the last lecture, the refraction will never exist without absorption. If there is refraction, if there is linear bifrigence, we can also talk about the effect of linear dichroism. And linear dichroism means that if absorption coefficients at one wavelength are not mutually equal, refraction coefficients at certain wavelengths are not mutually equal, it means that absorption coefficients somewhere in the spectrum or should be not mutually equal as well. So this is what Kramers-Kronig relation implies, and this is what we call linear dichroism. So it's basically different absorption for two differently polarized, linearly polarized waves. And a classical example of linear dichroism is a Polaroid glasses. As you can see, the light from the sun is unpolarized, and the light from natural sources of light is polarized, but it can get polarized by reflecting from surfaces. And in order to get rid of the light which was reflected from surfaces, like from the sea surface, for instance, we can use Polaroid glasses. We can use this special material which absorbs light of a certain polarization, and then in this way decrease the intensity of light reflected from the surfaces. If you work with anisotropic media, it's very convenient to use the following representation. So it's very convenient to work with vectors which would characterize the state of light. So imagine I have light, and light propagates along z-axis. Again, I'm working with a matrix 2 by 2 as an optical property. And as we saw already, if the refraction coefficients for light polarized along x-axis and refraction coefficient for the light polarized along y-axis are not mutually equal, then we have to take this into account in the propagation of light. In particular, it will result in a change of the polarization. So if linearly polarized light enters the medium, which has the property of linear bifrigence, and experience different refraction coefficients for different polarizations, at the end the light will not be linearly polarized anymore. It will have some arbitrary polarization, and in particular it may have some elliptical polarization described by, for instance, general expression shown just on this slide, where x e y would be equal to where z is the distance that light was traveling through the crystal. So from here you can also see that upon traveling through the crystal, the polarization of light can change. In particular, it can become, even if it was not linearly polarized before, it can become polarized along x-axis, or it can be linearly polarized along y-axis. It can even acquire different polarization. It's called circular polarization. It can become right-handed circularly polarized or left-handed circularly polarized. The expression for the waves in this case, these expressions are shown on this slide. And actually, when people looked at these very simple expressions, they figure out that we can simplify them and get rid of this oscillating part, I omega t, and write very simple expressions for the vectors, for the polarizations of light, which would be expressed in terms of vectors. So here, probably you've heard about this formalism. On this slide, I would like to show you a few ideas of so-called formalism of John's matrices. If you want to understand how the polarization changes upon propagation through whatever medium, you can use the formalism of John's matrices, where whatever polarized light will be represented by a vector, and the examples of these vectors are shown on this slide, and every optical component will be represented by a matrix. So as you can see, we can talk about linearly polarized light along x-axis, and it will have its own John's vector, or right-handed circularly polarized light or left-handed circularly polarized light, and will have a specific wave vector. Then if you have a situation when light propagates through a number of optical components, like component 1, component 2, component 3, component 4, and how many components, I don't know, could be as many as you like. You assign John's matrix to every of these components, and if you know John's vector that describes light at the input, you can calculate John's vector that will describe light at the output, following very simple expression from linear algebra. And we can define, of course, matrices for each of the optical elements. And for instance, if you're talking about bifrigent medium that has different refraction coefficients for light polarized along x and y axis, it will have a very simple diagonal form. Also, polarizer, like in Polaroid glasses, will have a specific Jones matrix. If polarizer allows light going through polarized along x-axis, it will have Jones matrix with 1 at the top left corner. If the polarizer allows light polarized along y-axis to go through, it will be the Jones matrix with 1 in the bottom right corner. So as you can see, again, talking about interaction of light with anisotropic media, the only complication we had is the transition from scalar to matrix, but at the end, if you know linear algebra, it doesn't create so many problems, because instead of scalar, we will work with a Hermitian matrix, epsilon, and instead of scalars as electric fields, we will work with vectors, and we will also we can model media using Jones matrices. So with this, I would like to arrive to a conclusion. If a medium is anisotropic, linear optical properties of the latter are described by a matrix of optical susceptibility or matrix of dielectric permittivity. In the case of non-dissipative approximation, the matrices are Hermitian matrices. And if light propagates through or bounces from an anisotropic medium, the original polarization of light can change. Thank you very much for your attention.